Right. Hello, everyone. Welcome to this talk today. My name is Luis. I work with JFrog. I'm a software lead, and I work with the content team. So as you can imagine, this is all about packaging today. So let's just jump right in. ARM devices. So cross-building C++ projects is hardly a new concept, but I think recently it's becoming a lot more popular, especially like in Conan we get in the issue tracker, a lot of users asking about support for cross-building. So while we may associate like cross-building with embedded devices, I think the reality is that even with the release of new Apple Silicon Macs, and I know Windows and Microsoft are making efforts to like have full-fledged support for Windows on ARM devices as well. And enthusiasts are really using NVIDIA Jetsons and Raspberry Pi for low power applications as well. And of course, I mean, we've probably been doing it for over 10 years now, but we have smartphones, and the workflow there when we have to build native code is always to cross-compile. But still, our developer machines are mostly Intel x64 based. So today I'm going to just go through an example of, we have a C++ project. It's a CMake project. We have some dependencies, and let's just assume that the project is already cross-platform. It already builds for a number of operating systems, and all of them are on the Intel architecture. I'm also going to assume that there's no, in our source code, there's nothing that is architecture specific to Intel as well, right? So it's generic, it's agnostic. So the goal is, can we build our project? And in order to do that, can we build the dependencies? So as an example, let's say we want to target Linux on 64 ARM. So how do we approach this? If we have the option, we can actually build this natively. Some devices that are running Linux and are running ARM as well, they just have a completely like full-fledged toolchain. So Raspberry Pi is one of them. You can install Ubuntu 22.04. I think you can also install a Debian-based Raspberry Pi OS, if I'm not mistaken. So we could just flash the OS, install a native toolchain, and then just build our dependencies and build our project. But how about cross-building? So, as I just mentioned, we have a choice of building this on the device itself, or we can also cross-build it from a different machine. So what we're going to need on that machine, and the example here would be Linux on x64, we have a cross-build toolchain, and we also have the ability to build the exact same project. And if everything works correctly, we get exactly the same output. So we will get the same binaries as well. Now, why cross-build? And there's a number of reasons why we might want to do this. Perhaps the most obvious one is that not all devices that run on a different platform have a native toolchain, right? We don't have, I don't know, on our iPhones or Android phones, a terminal with GCC installed or Clang. I wish we did. We could be compiling on the bus. Compile times as well. So it depends on the device, obviously. I know, like I've read, especially that the latest Raspberry Pis are actually quite fast, and obviously Apple has released these Apple Silicon, which are much faster than anything that came before that. But for some devices as well, that maybe for low power applications that were maybe more limited, we may want to just cross-build because it's much faster, right? On some devices, maybe we have like a vendor that they have given us a tool chain, and it only works if you port the project to a specific project format, right? On a specific special IDE that they give us. And maybe we don't want to do that. Maybe we want to continue using our CMake scripts and our current workflows. Hardware availability has also been like a massive issue. I managed to like buy a Raspberry Pi 4 this summer after 8 months of waiting. So Believe me, it was not easy. And then maybe continuous integration. Maybe we already have a project, it's already ported, it's already working, it's been tested, and we just want to make sure that as our developers make change to the code, we can at least guarantee that you can build it from source, right? And given the choice of making a Raspberry Pi 4 a build agent and an AMD Ryzen-based machine, I'll probably go with the latter. So let's say cross-building challenges. So I'm going to start going through some examples of what we might face when we try to do this. So for the simplest of cases where we have a dependency that builds a library, for instance, right? The build system tells the compiler to read the source code and output a file, right? So if we tell the build system, hey, use a different compiler that outputs code to a different architecture, that should just work, right? So that's probably like the simplistic case, and it's not in practice the sort of complexities, but like in reality, and at least having looked through this, this is from one of the Raspberry Pi forums, and it's relatively recent message. It's like, is there a current cross-compiling tutorial for Raspberry Pi 4? And this poor person, they said they gave up after 3 days of compiler hell, right? What surprised me was like one of the replies is like, if you want to like have fast builds, get another Raspberry Pi, connect them together, and set up a distributed compilation cache, right? So that's going to be my talk next year, but today I'm going to focus on this one. So imagine the frustration of actually somebody going through that. And for me, it's like, I'm not sure how good advice that is, because you have to wait like 8 months to get a Raspberry Pi. But it's not that much different, for instance, with the NVIDIA Jetson, right? So again, the NVIDIA support forums, we have a user that wants to set up a cross-build environment on Ubuntu. And one of the replies from NVIDIA is, well, TensorRT depends on many more packages. So, we actually recommend that you build on the device, right? So the NVIDIA Jetson, depending on which variant you get, they're not that slow, so it may actually be practical. But the thing here that kind of catches my eye is because it has dependencies, right? So, and dependencies, and I'm going to move to this one. These are the results of the recent C++ developer survey earlier this year, where one of the questions was, what are the top developer frustrations, right? And the top one is managing libraries that my application depends on. So as usual, this is not surprising at all, but when it comes to cross-compiling, I would argue that this is even more challenging because of some of the issues that we may have. So let's just get started with our project. So as I mentioned earlier, we have our project. It's a sort of a vanilla CMake project. Everything is cross-platform and agnostic, and we have our dependencies. We have been given a cross-build toolchain, and this includes a compiler that will output code in our target architecture, but also the BNew tools like the linker, the assembler, and the libraries required to actually generate this code. And before moving forward, I just want to mention the terminology that we may find in different tooling as well. So we have the GNU convention, which is the build machine is the machine where we are performing the build. The host machine is the machine where the code that we build is going to run on, and then the target machine, this is typically only mentioned in the context of building a compiler, when it might differ, like where the compiler might run on a platform and it may be producing code for a different platform. So that's not the topic of this talk. And what I want to mention in particular is that different tools in the C++ world use different terminology. So Conan actually has chosen to use exactly the same terminology as the GNU convention. So we have build for the machine doing the build, and host for the machine where we're going to be targeting. VC package, on the other hand, is using host for the machine we're building on, and target for the machine we're building for, which is similar to what CMake actually does. So some of the variables in CMake that control these things are actually CMake_host, right? So we have an unfortunate situation here where the term host actually has opposite meaning depending on which tool you're using. So this is again something that we get in the issue tracker a lot because people have preferences. Unfortunately, I think we're already pass the opportunity to actually fix this, so we always try to clarify. So, you know, recent like modern C++ projects, we may already be using a package manager, right? So for instance, in this, you know, hypothetical CMake project, we may run con'd install and to generate the toolchain file that we can feed to CMake to actually get all dependencies, right? In VCPackage, for instance, the workflow is very similar as well. So what we want to do is keep that workflow to actually handle our dependencies for the platform that we want to build for, right? So in con'd now we have the features of like two profiles. One of them is a host profile, which is the one for the machine that we're building for, and the other one is a build profile that models stuff that we need on the machine that we're building on, and I'll elaborate on that a bit later. In VCPackage as well, there's also the ability to specify a target triplet, so you may be able to like customize what triplet you're using to target your code, right? So speaking of the compiler, this is how it's all gonna start. Con'd and VCPackage let us build dependencies from source if there are no binaries for them yet, right? So what we need to do is use the functionality provided by con'd and VCPackage to actually, you know, tell those dependencies and their build systems, hey, build for this other platform, right? So as I mentioned earlier, we have the simplest cases. All we need to do is just point to a compiler that will output to a different architecture. So with GCC and Linux, a lot of the tooling will just inspect the value of the CC and CXX environment variable. Apple Clang, it's already a full-fledged cross-compiler, so you can just add a flag to control which architecture you're building for, and it will take care of everything for you. And Windows on MS with Visual Studio, you can set up an environment similar to how you do it on Linux, and basically, or via CMake, you tell CMake which toolchain to use, and that should cause the code to be generated for our target platform. The build system needs to be aware that we are in a cross-building scenario, right? So this is where things start to get a little complicated. So if we're using auto tools, that requires passing those two flags during the configure phase. And if we're using CMake, CMake will understand that it is cross-compiling if CMake system name is being set manually, typically from a toolchain file. The reason the build systems may need to do this is because a lot of them, during the configuration phase, they will build like test projects. So they will actually compile code and run executables just to maybe query for features of the compiler or the SDK or the system. So this is obviously when your compiler is writing code for a different architecture that maybe you cannot run on your own machine. That's not going to work, right? So that's why this is needed. So first sort of strategy that I want to propose here is like leverage the package manager to specify the compiler to the dependencies that you want to build, right? So both con'd and VCPackage allow passing custom options to the underlying build system. So we can do just that. So I'm going to show you an example on how we can do this with con'd. This would be an example of a profile modeling the native toolchain, right? So this is actually for my own laptop where I'm running Apple Silicon on M1 chip, and I'm currently running Apple Clang version 13. But now I want to be able to like have a con'd profile that has the settings to be passed for me to generate Intel x64 code, right? So this is what it would look like. So as you can see at the top, I'm changing the architecture is x86-64, but all it does is that's just me expressing what I think the output of those binaries is going to be. But the configure section at the bottom, that's actually is how we tell the underlying tools, you know what, this is the flag that you need to pass to Apple Clang to build code for x64, right? There's other things. We can actually edit some of the variables that we pass to the generated CMake toolchain by con'd. So the idea is that you don't have to change or patch the build systems of your dependencies or even your one to start this build, right? So it should be just handled for you. So that's that configuration bit there. VC package, if I'm not mistaken, you can have your custom triplets as well, and it has an interface. We can define some variables in those triplet files that will be passed on to the CMake toolchains. So, as an example, let's say I want to build a ZLIB, and I want to build it both for on my machine. I want to build it for Intel and for Apple Silicon, right? So, this would be a command invocation. To build it natively on M1. And as you can see, both profiles are basically exactly the same, right? And with both profiles are the same, all the settings are the same, it just means a native build. But now I want to build it from my Apple Silicon MacBook to Intel. So the one that I'm changing is the host profile, which is the one that I'm generating code for, and I'm leaving the build profile exactly as it was before. So if I run these two commands and then I query Conan for the packages for ZLIB, I can see that it has generated something, but we still need to verify that the code, the actual binaries are correct. So we can use some of the Apple utilities to say, hey, can you tell me what architecture this is, right? So the Intel one is obviously Intel, and the ARM one is ARM, right? So it's basically, or it should be, as easy as that, right? On Linux, on the other hand, things are not as simple as telling Clang to just use a different architecture. So you may want to you may be given, a completely different compiler toolchain, right? So as I mentioned before, this includes the compiler, the binutils, the linker, the assembler, and also the system headers and the standard libraries to link your binaries with, right? So another proposed strategy here is package up your compiler toolchain, right? And what you can do here is like a profile like this is going to cause Conan to load that package whenever it needs to build anything, right? So that's what tool requires means in this instance. And that package has information that it propagates to consumers when they're using this package to build something, right? So in this case, it's going to be those environment variables that I mentioned earlier that build systems on Linux typically need to know about to build for a different platform, right? So, and at the bottom as well, we also have like a CMake toolchain integration. So by defining the system name in the toolchain manually like that, that's going to cause CMake to know, hey, I am cross-compiling. So the example I've just shown you now, if we were to do this, is that we're able to cross-build ZLIB, for instance, and generate the shared library for it. And we could also be operating, let's say, on a Raspberry Pi where we have access to the native toolchain and we don't have to define any special variables. And we should be able to generate exactly the same binaries, right? So if we're operating in a way where we're perhaps using a repository to cache our binaries, you can cross-build them, and then a user on a Raspberry Pi could download them, or vice versa. You can generate on a Raspberry Pi if the times are not too bad, and you can upload it, and it should just work. Where it starts to get interesting is the executable dependencies, right? So if you look at this, while we are passing the specifying to Conan, oh hey, this is the build profile, right? We're not using it here at all, right? But when we have executables as part of our build process, that's when this gets interesting. So a lot of the dependencies are likely to be libraries, but during the build of our project, we may have to call an executable. Maybe we have a code generator. Maybe we have a tool to patch a file after it's been generated, right? So that's when the concept of the build context and the host context actually makes sense. If, as part of building something from source, we require an executable for our current build machine and not the target one, this is how Conan would model, hey, I actually need to get a different binary. So the way we can do this, and both Conan and VC package support something like this, is you have two types of requirements. Requirements for the host context, which is the machine that we're building for, and requirements for the build context, which is the machine we're building on. And that's what tool requires means in this instance. So, and let me see here. And this is now, if we're cross-compiling and we're specifying two different profiles for this, the tool requirements would come for, in this case, natively for ARM or Apple Silicon. and the host ones for Intel, which is what I'm trying to cross-build to. PC package has a very similar feature where you only need to specify, and like I said before, host is what they call the machine doing the build. So if you have a dependency that needs to be in the host context, according to their terminology, that's how you would do it in their JSON files, right? Now, the interesting thing, and I want to mention this, is like, if we're already building natively, let's say I'm building natively on my Apple Silicon MacBook, when I'm cross-building for a different architecture, it's still using exactly the same executables. So all those executables I need to run at build time, they're going to be the same on both if I'm doing those two builds on my own machine. But things start to get even more complicated. So far we have seen packages that had only executables or only libraries. But there are situations where we have executables that are coupled with some libraries, right? Protobuf is an example. The Protobuf compiler, it will generate some code based on some proto files, and then you're going to compile that code, and that code needs to be linked against the Protobuf library. So when you're cross-building, you're going to need Protobuf compiler for your current build context, but the Protobuf library, you're going to need it for the host context, right? I think Qt is similar as well, where you have some utilities like the meta object compiler. I think that's what MOC stands for, but the libraries are obviously going to be for the host architecture. So we may end up with something like this, with packages that contain executables and libraries, and we have to we're kind of exposed to both during a single build. So how do we model this? So another strategy proposal is you can actually have, at least in the recent versions of Conan, the same requirement in both contexts, right? So you can say, I require Protobuf for the machine I'm targeting, but I also require Protobuf during the build, right? Now, in this case, Conan knows about this, so it will only expose the library from the host context to your build, and it will not expose the library from the build context to when linking, for instance, right? So that would avoid the situation where you may be linking against the library from the wrong architecture. So if you have a Conan file that has requirements like that, it will work, right? In this case, I'm actually using the latest Conan 2. But as you can see here, two different binary packages of Conan have been pulled to support this, right? But there's another strategy that, and it's something that I came across by inspecting what Debian or Ubuntu were doing. It's like, depending on the situation, you may be able to split the packages for the executable and the library. So what I mean by this is I could have a package called Protobuf compiler that only has a compiler, and I can require that in the build context. And I can have a package for the lib Protobuf, right, which is the one that I need to link against. And my requirements would now look like this. I require lib Protobuf to link against, but I require the Protobuf compiler during the build, right? And as I mentioned before, this is nothing new. This is actually how Debian-based distros do it, and have been doing it since those days where we actually supported both Intel 64 and 32-bit, where the system can have libraries for both architectures, right? So that's been extended over the time. So you can actually install libprotobuf for Intel and also for ARM64 if you want. And both the native toolchain and CMake, if I'm not mistaken, they are aware of this. So when you're cross-building, they will use a different suffix for the libraries, right? So it can still work, but you'll find the right executable that you need to run during your build, and use the right library as well to link against. So this approach may not always work, and that's what I'm going to discuss next. I'm calling this cross-architecture tooling. I'm not sure that's the right term, but hopefully I can illustrate what I mean by this, right? So there are some tools where the executable where we have an executable that is tightly coupled with a library, right? That it needs to access a library, and the executable running on the build machine. So if we're cross-building from Linux x86 to Linux on ARM. The executable around running on build machine has to interact in some way with the file with the target architecture, right? a very obvious example is actually the linker. I'm running the linker on my build machine, but the linker needs to actually process the files for the ARM architecture, right? And not only that, but like it, in particular, the linker or the compiler are going to implicitly link the C++ standard library, for instance, which is part of the same package. So now we actually kind of have a package that is doing both. We have, interacting with the two different architectures, right? Files from two different architectures, sorry. So the CUDA compiler is another example as well, and it's actually what this diagram is about. I can use the same CUDA compiler to target my native x86 machine, or the same CUDA compiler will, and it will load the libraries or interact with the libraries for x86. Or if I'm cross-building, right, and the CUDA compiler will be the same, but the host compiler will be different, now we'll want to load or interact with or know about the libraries for ARM, right? And I'm talking about the CUDA toolkit libraries and the runtime. So how do we approach this, and how can we potentially package these, right? A potential solution is basically package that executable that runs on the build context with both sets of libraries, or all the sets of libraries that we may want to support, right? So this would be the build context when on Intel, and we could have another one, the build context when on ARM, right? And it would allow that. So, but as I mentioned before, when you were doing this, Conan was smart enough to not expose the libraries from build context tools to your host context, right? So there's actually a feature for the integrations when we generate the CMake files to resolve things like find package and stuff like that, to actually do that. But in this instance, because we have libraries for two architectures in the same package, we actually may have to add conditionals in some of the kind of recipes to say, hey, if you are in the build context, and you're targeting a different architecture, expose this set of libraries, and if you're not, expose this other set of libraries, right? So it becomes complicated, and unfortunately, I don't really have much of a solution, but I know it works, right? The problem is that there needs to be a more canonical solution, in my opinion. So something that we could do, takes me to the next slide, is like, let's say one of these tools has a problem. Why don't we do the same like we did with protobuf, right? But unfortunately, this is only possible if the actual executable gives you a way of pointing at the libraries that it's looking for, right? So we have all the information in Conan if we do it this way. So we know where the executable is, and we know where the libraries that the executable needs are, right? So what I found, especially with both the Qt tools and the CUDA compiler as well, is that they have internal logic to locate the libraries relative to where the executable is, right? So it can be tricky if you actually now decide to, hey, I'm going to split these libraries and the executables, right? But on the other hand, the alternative is that you would have what we had in this slide, which is you have a package that actually has libraries for multiple architectures. So, but both are technically possible depending on what's allowed, right? And here I'm actually saying generic toolchain, right? There's actually a very common case where you are allowed to sort of overwrite the library directory from and read it from a different location, right? So our goal would be something like this, where we can require the libraries in the host context and the executable from the build one. And a very common example of this is actually the Sysroot flag in some of the Linux tooling. So I mentioned before that we have a cross-build toolchain that contains the compiler and the linker, the assembler. Also includes it also has the include files for the standard C and C++ libraries, and potentially I think also the C and C++ standard libraries. But in some workflows, you can actually override where it loads the include files and the libraries from a different location. That's what the ---- Sysroot flag does, right? So this is very typical in embedded Linux, where this is like a root file system, which is a copy of what the file system looks like on the actual target device, right? we may be given this, or for Raspberry Pi, there's like really interesting instructions on how to generate this, right? But perhaps like more enterprise ready solutions, we will be given something already that we can use, right? So what happens here is like this flag actually has the effect of telling the compiler and the linker, hey, when you need to include something, reroute the search to this Sysroot as well, which can come with some problems as well. So because there's no standard Linux SDK and every distro can decide to include different sort of libraries depending on what they decide to include, you may have dependencies that your build system is now exposed to, right? So if they include ZLIB or if they include OpenSSL, and you also had them as con'd packages, right? Because that's how you did it on your other platforms. So especially if you're using CMake, this can cause a bit of an issue where CMake is going to look first in the Sysroot and then in all the other paths, right? So here, my proposed solution, well, two proposed solutions as well, and I think I'm becoming repetitive when I say that we should package everything. We can have the compiler toolchain in a package, which is going to be the executables, and we can also have a root file system for the particular device that we want to target, and then for that second one, we could specify that it will append these flags to the compiler and the linker to reroute the search. And what I would advise is if you have system dependencies that are on the Sysroot, use them from the Sysroot and not from con'd NVIDIA package. Or if you know that you don't need it for anything else, delete them from the Sysroot as well, so you can actually use the ones you want. That would avoid most of the problems. And then a solution like this, basically the profile that we had before, we already have the compiler there, and now we have the the Raspberry Pi Sysroot, for instance. So if that's what I want to target. So I think with all these things now, we would be ready to build our code. Like if we call con'd like I mentioned earlier, and both con'd and VC package would give us the option to say, hey, you do this the first time. The dependencies for the architecture, I don't have the binaries for, and build them from source. And if all the things are right, they would just be fed to the particular places, and it should just work. So I think perhaps a summary of what I'm proposing is just basically package all the things, including the things that you don't regularly package when you're building natively, because that's already part of your system. And this has a lot of advantages, like you may have a lot of developers in your team that need to do this workflow as well, so it can just work. So maybe you have at least you could have a developer that is building on one folder, is building for their native architecture, and then in another folder is doing a cross-build, right? Now, what's the usefulness of this? Because then you need to run and sort of move the binaries across and run them, right? So that depends on how you structure things. But there are you can also leverage the package manager for this. But that would be the topic for a completely different talk, because it's an interesting thing. If you simplify things and you link libraries statically, and you don't have dependencies other than what's already on the system, you could just copy the executables across like via SSH or something, and you could run them. Or you could sort of try to, remote debugging or something like that. For me, one of the most useful things about this could be CI, where everything is already working, and I just want to ensure that no code changes from anybody in the team are breaking any of the supported architectures. And then as for closing remarks, so as I mentioned, we can leverage the power of modern C++ package managers to actually sort of inject and prepare the environment to build your dependencies, but also your project in a way that you don't have to modify your project to support this, right? To me, that's very important, because I was looking at the instructions on how to build, I can't remember, it was OpenCV or Qt6, and OpenCV has like a lot of CMake toolchains already that they already support. To be honest, it's amazing work. It's really comprehensive. But it means that you have to care about those things, right? If your project is agnostic and is sort of generically cross-platform, you shouldn't have to worry about this. now that both Con'd and VC package use CMake toolchains, they can do it for you, right? So we can retain our existing workflows. We wouldn't have to say, I was given this toolchain by a vendor, but they want me to use this particular IDE. So do we want our developers to have to port our existing build system to something else just to cross-compile? Assuming that the actual underlying compiler that this IDE is using, you can invoke it independently. So what I'm trying to say is, you can offload the heavy lifting to the package manager, but and cross-building, in my opinion, and I'm happy to be challenged on this, is basically a dependency management problem, right? Because you can look at the compiler, the link, everything. You can look at it as a dependency just to get started. However, Con'd and VC package already work like this. Con'd and VC package, they create the environment for your build system to find the binaries where Con'd and VC package want you to find them, right? So how or why should cross-compiling be any different? But we have challenges with dependencies. If they're library only or executable only, they are easier to handle. But if you have executables that are tightly coupled with libraries, whether it's protobuf or Qt or the CUDA compiler, it can be tricky. It can be solved. It may be like a big one-time effort, but it's possible. And once you get past that initial hurdle, things definitely become a lot easier. And that's it. Thank you so much. Any questions?